Hello and welcome. This presentation is a summary of data mining methods used to predict whether potential borrowers will default on their auto loans. Auto loans are granted to consumers every day to front the cost of buying a vehicle. It's a lucrative business because customers often cannot pay full ticket price upfront for vehicles since they're large purchases. Lenders make money by collecting interest on these large loans. But not all loans make money because sometimes borrowers miss payments or default on their loans. There's no guarantee that lenders will get their money back, not to mention their interest, if borrowers cannot make their payments. For this reason, we set out to predict if an applicant will default on the loan they're applying for. The data we have to input into our model is data supplied by the customer, as well as credit history information included in the loan application. We're most interested in identifying borrowers who will default, because granting their loan would result in loss for the lender. We want to maximize being able to detect that outcome. The three main questions we hope to answer with these models are shown here. Number one, as mentioned previously, our main objective is to identify defaults, given the application information we have. Number two, ideally, a model can perfectly predict whether a borrower will default or not, and the lender will always be able to make the right decision to lend to them or not. Unfortunately, perfect prediction is not usually attainable. One question to answer is whether the information collected on a loan application will be able to predict borrower behavior to a satisfying degree. And finally, number three, even if we don't come up with the perfect model in this iteration of modeling, can we at least determine which variables seem to predict the target the most for future modeling? This data set we collected for this project came from Kaggle.com. The raw dataset had 233,154 observations and 41 independent variables, including the target variable loan default, which is a binary target that indicates if the borrower ever missed loan payments. Remarkably, it boasts no missing values. For initial data cleaning and preparation, we removed all identifying information about the applicant and only kept relevant inputs that related to the loan and the credit viability of the borrower. We then ran stepwise regression for further dimension reduction, reducing the inputs to 14 meaningful variables. We ran 3 models with the original 233,154 observations and 14 inputs, and noticed severe underperformance in ever predicting when the target variable equaled 1. So we circled back to cleaning the dataset and utilized balancing techniques to get an even 50-50 split between classes. We'll go into more detail about the 14 variables and the balancing techniques in the following 2 slides. As promised, this data dictionary defines the 14 variables produced by stepwise regression, which became inputs in all future rounds of modeling, plus the target loan default. The input variables are the age of the customer, the cost of the vehicle or asset, the average loan tenure in months of the borrower's credit profile, the amount of time also in months since their first loan, the number of loans they've defaulted on in the last 6 months, the dollar amount of the loan disbursed, the employment status of the borrower, such as salaried, self-employed, or not applicable, the ratio of the loan to the value of the asset, the number of loan inquiries made by the customer's numerical representation of their credit score, the description of the borrower's credit score, such as good or excellent, the number of active loans in their borrower history, the number of defaulted accounts, also in their credit history, the total amount sanctioned for all loans in their borrower profile, and again, the dependent variable, the loan default, which is 1 meaning they did default, or 0 meaning they did not default. As also mentioned before, the first run of each of these models all predicted very few borrowers to default, which is not helpful given the main goal of the project. Almost 99% of the borrowers were predicted not to default. Revisiting the observations, it was clear that the original data was also imbalanced. Just over 20% of the observations recorded a loan default, leaving about 78% not defaulting. While the actual split between the classes is closer than the predicted totals, it is possible that this original imbalance is being carried forward into the initial models. we could be inadvertently overweighing the observations where loan default equals 0 by them accounting for almost 80% of the inputs training these models. In other words, we were potentially oversampling the majority class. In order to weigh the minority class more heavily, we decided to reevaluate the set after balancing the observations to an even 50-50 split. We kept all observations of default, which totaled 50,610, and randomly sampled an equal number of observations that did not default. This left us with a dataset of 101,220 total observations. Here are the modeling techniques we used in both rounds of modeling. We ran a nominal logistic regression, built a classification tree, and developed a neural network. All three techniques were run on both the original and the final dataset, with the 14 inputs identified with stepwise regression. After running the three techniques again, we produced many more predictions in both classes for all three models. More details on each of these models can be seen in the written report. Here we see the R-squared value, the root average square area error, the sensitivity, and the specificity. The R-square is the overall prediction of the value of the model, which can range from 0 to 1. As you can see, these numbers are very low. Root average square error is an evaluation of error in the model, and sensitivity and specificity are important for their indication of how good the model is at predicting members of each class, either positives or negatives. In the longer report, we also discuss accuracy, precision, and AUC, which is another error statistic. One of the takeaways from these results is that the models all performed poorly in predicting the target in terms of model fit. Moreover, they all performed similarly poorly, with the neural network performing slightly better in all metrics. This is also true of the additional metrics that are included in the written report. It's important to note that the sensitivity, or true positivity rate in predicting defaults, is correct 65% of the time. This is better than the results before balancing the dataset, which were just over 50%, or a little better than a coin flip. With more observations predicted to default and a higher sensitivity, this is an improvement from the first round of modeling. It's also good to see sensitivity higher than specificity because we would rather detect a borrower will default, positive outcome, than a borrower will not, a negative outcome. In terms of cost, it's better to have fewer false negatives than false positives, which this comparison indicates. A false negative means the borrower did default when they were given a loan, which is costly. This costs more than a false positive, which means a customer was not granted the loan, but they would not have defaulted. The classification tree did produce some answers to our third initial question about the predictive value of the inputs. It indicated that the top 4 inputs were the ratio of the loan to the value of the vehicle, the borrower's numeric credit score, their ordinal credit score description, and the number of loan inquiries on their recent credit history. In conclusion, all the models performed poorly by fit statistics, such as the R-square value. Of the models, the neural network performed the best in all metrics, but the difference was negligible. Balancing the data set improved the model's ability to predict borrowers would default on their loan. The classification tree helped gain insight into the predictive power of some of the most influential inputs. And one more note, that the logistic regression model showed correlation between self-employment and loan default. This information is especially helpful for future modeling and digging deeper into that potential connection. However, with a misclassification rate still over 40%, we do not feel that these models are ready to be deployed. However, these conclusions can be carried forward into future iterations. If we or another team were to iterate over this problem again, we would look closer at the data for some of these anomalies in relationships. For example, we took note that the average age of borrowers was 35, but many of them had no credit history whatsoever. This seems incongruent and is worth investigating whether this is an anomaly from missing or imputed values or a real phenomenon that many adults do not have a significant credit history. Given that credit score and credit description are influential inputs, just improving visibility into credit history may help the predictive power of this data. Also, there's a high instance of borrowers not defaulting in this data set. It would be helpful to apply these techniques to a different data set and see if some of the same patterns emerge or if this is unusual. As introduced in the previous slide, there is opportunity to still iterate over this problem. If we were to further model this data set, we would first reassess the validity of the data for missing or imputed values, given some of the trends and anomalies we saw. We would employ balancing techniques to weigh the minority class more heavily, since it's more important to the business objective. And finally, we would recommend using the neural network technique, given its better performance than the other models considered. Thank you for taking the time to listen and watch our presentation. We hope you enjoyed it.